So, in the algorithm, this output is 2 raised to t plus 0.5, right? Maximum value of z is t. So, that is our d hat. Now, let us compare it with 3D and d by 3. So, let a be the smallest integer such that it is just above 2 raised to a plus 0.5 is just above 3D. It is kind of log, we are looking at log of 3D, okay. And similarly, or symmetric thing is, let B be the largest such that 2 raised to B plus 0.5 is just behind d by 3. Okay, this is again B is kind of log of d by 3. Now, we want to compare t with a and b, how much or difference is possible. So, first is the probability that d hat exceeds 3D, right, which means that t exceeds a. So, what is that? So, if t exceeds a, then basically y a is positive, and positive means since y a can only be an integer, so it is at least 1. Now, what is the probability that this random variable y a is 1 or large? So, that there we use concentration inequality. So, you can write this as bounded by expectation of y a by 1, right, that is Markov inequality. So, expectation you understand d over 2 raised to a. Now, what is d over 2 raised to a? So, the way we defined a, we actually get a bound square root 2 by 3, that is less than 1. So, the chance that d hat the output exceeds 3D, it is more than 3 times d, is sufficiently away from 1. Okay, this is what we learn. And similarly, we can do the other part. So, probability that d hat is less than equal to d by 3, right. This is probability that d hat less than equal to d by 3 means that t is smaller than less than equal to b. Which means the way we defined y, it means that y b plus 1 is 0. And what concentration inequality should be used here? So, we can use here Chebyshev inequality. So, you need knowledge of variance and expectation. So, probability that y b plus 1 minus the expectation of b plus 1, right, y b plus 1 is 0 and expectation is d over 2 raised to b plus 1. So, there is enough gap, that is what we will utilize. So, what is the chance that there is this gap between y b plus 1 and its expectation? So, that chance is limited by variance. right, which is, so variance is in fact this d over 2 raised to b plus 1. So, this is 2 raised to b plus 1 by d, and 2 raised to b plus 1 by d comes out to be again square root by 3. Right. So, in other words, what you have now is probability that d hat is smaller than, or say, yeah, it's between 3d and d by 3, right. This is at least 1 minus 2 square root 2 by 3. Okay, that's positive. So, there is a good chance that the algorithm is actually outputting and a good estimate for d, but this probability is not close to 1, right. It is more like close to 0, although it is a constant, positive constant. You can actually boost it by the boosting trick. So, the probability can be made 1 minus 2 raised to 1 minus 2 raised to minus k, which means as close to 1 as you want. Okay, you can boost the success probability by running k independent and parallel copies of the algorithm for the stream. Okay, the independence part is important, which means that you, instead of picking one hash function, you pick k hash functions completely independently, and then use this valuation trick. So, you will have k many t's that you will get in the end. And what do you output as d hat? Yeah, so there is a nice trick. You output the median of these k answers. And output the median. Okay, so not the least t or the maximum t out of these k, but the median. So, the advantage is that you can show that the median being far away from d, that probability you can bound by Chernoff bound. So, Chernoff will give you the theorem that the output is between d by 3 and 3d is quite high, as high as you want. And how much space is needed? Well, log n was for the algorithm, so it's k times log n now. Okay, so so k you can take to be 10, and then the success probability is almost 1 for the output approximating the distinct elements, number of distinct elements, while the space is still constant times log n. Okay, so that's an amazing algorithm. When we started, it was not clear whether such a thing will exist, but it does. Okay, so that's the first algorithm in data streaming. Second question that we will take up is whether there is an element in the stream that has a very high frequency, okay, which basically suggests in applications it could suggest an attack. Okay, some token is appearing too many times, too many requests coming from that client. So, detecting a heavy hitter. So, we want to check whether sigma has elements of unusually high frequency. So, perhaps it is an attack on the server. Right. So, this kind of I mean, when you have a server and a client and many clients are making a request, this algorithm can be used, can be seen as a way to detect whether one client is sending too much of data, too many requests compared to other clients. Okay, so then you can decide to just ban that client. So this client is called heavy hitter. How do you detect a heavy hitter? Again, in a very long data stream, right? You cannot really remember what that client did because there are also many clients and there are many requests. So, in terms of data stream model, what you want is now you want to work with frequencies. So, let Fj be the frequency of j in the stream sigma. So, what is summation of all the frequencies? So, summation of frequencies is m, right, that is the length of the stream. So, we call it the first moment f1. And the idea is for the algorithm compare f1 with the second moment. Which is sum of the square of the frequencies. Right. So, heuristically, if f2 is let us say very close to f1 square, let us say 0.9 times f1 square, right. If f2 is very close to f1 square, then it suggests that there is essentially one frequency which is very large compared to the others. Obviously, if there is only one kind of token, then f2 is f1 square, right. But if there are many tokens, then f2 cannot really be equal to f1 square, it will always be smaller. But it being close to f1 square suggests that something is wrong. There is a heavy hitter, implies that perhaps a heavy hitter. Okay, so comparison is fine. You can decide how to define heavy hitter in terms of f2, f1. This is just one option. But the bigger question is how do you compute f1 and f2? So, f1 you can compute just by keeping a counter, right. It requires log m space. How do you compute f2? That is the tough question. So, compute f1 by a counter in space log m, right. This is fine. the major question here, the only question in this problem is how do you compute F2? So, F2, the problem is that this is a non-linear expression. So, you cannot really divide it into token by token computation, right. This seems to need Fj in full. So, unless you have reached the end of the stream and you have calculated all the Fj's, F1 to Fn, it is not really clear how do you compute the non-linear expressions, right. So, counter is not clear. This indeed seems impossible to compute exactly. So, we will see an amazing algorithm again, which is by Alon, Matthias and Szegedy. So, the AMS 99 algorithm to compute F2 uses a hash function. A hash function h, like the previous algorithm, but unlike the previous algorithm, this will have a range plus minus 1, okay, which is very strange. It actually will assign a sign to a token, plus sign or minus sign, and hash function, the sampling condition is also tougher. It needs 4 independents. From 4 independent hash family, so pairwise independent hash family construction we have seen in this course. How will you actually construct 4-wise independent hash family? You really have to go beyond matrices for that. So, I will just leave as an exercise by using cubic polynomials. Modulo a prime. Okay, so it will be a different construction. These things exist, you can study them independently. AMS algorithm says that you pick a random 4 independent hash function h, which assigns signs to your tokens, okay, n tokens appearing in this long stream of m tokens. It will be h will be very compactly stored. Okay, you don't need its values on 1 to n. It will just be this cubic polynomial, so it will be very compact, and you can do computations as you see tokens in your stream. That is the beauty of it. So, first pick random 4 independent hash h compactly stored, initialize z to 0 for token j in the stream. Right, this is similar to the algorithm we did before. So, when you see token j in the stream, you compute the hash function and keep adding. Okay, that is it. So, you either will add 1 or minus 1 depending on image of h. Okay, so, you are actually adding these plus minus 1. So, in the end you may also have a negative number. Now what is the meaning of this Z, right? It's completely unclear. It's a magical thing. So the output, you simply output the square of this, okay. So Z may be negative, may be positive, but when you square it, it's always non-negative, and that is what you output. Now the question is, what is this to do with F2? So is Y related to F2, right? That is not at all clear in this algorithm. It's a very simple algorithm, but now all the work will be done in the analysis. So first property of Z is, which is actually the definition already in the algorithm, that for the stream or let me say J1 to N. So for these tokens, each J image of J under the hash function, this will be added as many times as the element appears, right? So that is Fj. That's by definition, that is what the algorithm is doing. And so what is the expectation of this? By linearity of expectation, you get frequency is fixed, that is not a random variable. Each J is but since H is randomly picked, Hj is either 1 or -1 with equal probability, right? So this is 0. So expectation of Z is what you expect Z to come out is 0, right? So Y, can you say the same thing about Y? Is Y also 0? Expected to be 0? Well, not quite. So that is what you will now see. It's a different game altogether. So expectation of Y is expectation of this thing squared, Z squared, right? So sigma Fj Hj squared. So that is expectation of so that inside thing is Fj square, sigma Fj square plus sigma Fi Fj, I different from J, x and Hi Hj. So expectation, well, sigma Fj square is just F2, right? So that's F2 plus, interesting thing is the second thing. So here by linearity of expectation, you take it inside. And in fact, I also factorize. I express it as Hi times Hj, expectation of first times expectation of the second. And why did I do that? So this I can do by, since I and j are different and hash function is 4-wise independent, in fact, so it is 2-wise independent. So because of that, I can factorize E, and then again this part is 0. So you see that this justifies our algorithm, right? Because although Z is expected to be 0, Z square is not. And this should be a big surprise, right? Somehow this probabilistic calculation is telling you that expectation of, or z square is expected to be what you wanted, which is f2. But now what is the guarantee that it will be close to f2 in practice? Right? For that we need concentration inequalities. So let's do that. But this actually tells you, at least tells you, that we are on the right track. So next what we will do is, for concentration inequality, we will compute the variance of y. So variance is y square minus expectation of y whole square, which is expectation of z to the 4 minus this. So expectation of z to the 4 is it's a complicated thing. So this is fj hj to the 4 minus expectation of y we have calculated, that's f2. Now the thing is that when you expand this out, fj hj to the 4, what you get is f1 times f2 times f3 times f4, right? 4 things. So if these 4 things, what if they are different, then point is that expectation will factorize. If they are not different, then it will not factorize. So when it factorizes, you get 0. When it doesn't factorize, then you are stuck with it. So you will be stuck with the following terms. So expectation of fj to the 4, right? Fj to the 4, you cannot do anything, it's non-zero. And second is when both, I mean, out of 4 things, so repetition is there. So let's say f1 square times f2 square, those kind of things. So that is fi square fj square. Okay, and there is, because of this binomial expansion, you will have a 3 sitting outside minus f2 square part. How did we get this? So this we got by using 4 wise independence. Okay, this is really using 4 wise independence. That's where we need 4 wise independence, because you can have in the binomial expansion f1 times f2 times f3 times f4. So you need expectation of this to be 0. So you actually need then expectation to factorize over this, so that it's 0. Now we have this highly simplified expression, and let us work it out. So this is equal to, I mean, we can take out expectation because these things are actually fixed, right? So you have sigma fj to the 4, then sigma fi square fj square minus the green term, which is what? So sigma fj square and fi square fj square. That is what f2 square is. So what you are left with is just 2 times fi square fj square. Okay, so that is variance. And this you can upper bound by 2f2 square. Okay, this is, you can see fi square times fj square is kind of coming from f2 times f2. So, we have this clear upper bound, and with that, when you use Chebyshev, so Chebyshev concentration inequality, it gives you that probability that the output y is away from the value that we want, f2. How much away? Some alpha times f2 away. So, that is variance of y, which is 2f2 square divided by alpha f2 square. Okay, so y minus f2, y being away from f2 by, let us say, 2 times f2, that probability is no more than half. Okay, so this is again going in a very good direction. It is telling you that you will have an approximation for f2. So, this means that y approximates f2 well, right. So, now we have guarantees, and the guarantee you can improve further as we did before. You can improve it further by running this algorithm independently and simultaneously. So, again what you can do is reduce the variance by keeping k independent estimators y1 to yk. Instead of computing just a single y, you compute k independent ones by obviously by picking k independent hash functions, 4 y's independent hash functions, and output. So, in the previous algorithm, in example 1 you outputted median. Here what you want is this Chebyshev bound to improve, right. So, you want a smaller variance. So, what you do is you actually take an average of y1 to yk. So, output y prime, which is the average. So, not the median. Okay, you output the average. So, this has the desired effect of expectation being unchanged and variance being, so variance, remember, requires squaring, right. So, actually you can see, you can show that this variance has reduced by k. Okay, so expectation does not change, variance becomes smaller, and hence when you use Chebyshev inequality, the RHS will be now much smaller. So, you will get the desired probability, and you can take alpha to be as small as you want, right. So, y will be very good approximation of f2. Okay. So, gives a much better approximation of f2 in space k times log m. Okay, so that's it. This finishes streaming algorithms, and in fact this finishes the course also. So, I hope that you like the theory and you also appreciated the applications. Okay, thanks.